So tutorial question number 2 in the energy booklet. First of all, extract the information as usual. Mass is 125 kilograms. Radius of gyration 150 millimeters or 0.15 meters. It's accelerated from rest, so we know that omega 1 is 0 radians per second. So that's worth remembering. Omega 2 we're not given, actually, even though it sort of implies it is, because it says a speed of that. Well, we're given the frequency, 1250 RPM. So that's actually frequency 2. Divide that by 60 and we get 20.83 hertz. So actually we need to remember that omega 2, the final angular velocity, is 2 pi times that frequency. So there'll be a little calculation required to actually calculate omega 2. We're given the number of revolutions, 500 revolutions, and it's worth remembering at that point that that's related to theta, because the total angle that you turn through equals the angle you turn through in radians for one revolution, which is 2 pi, multiplied by n, which is the number of revolutions. So in fact, giving you the number of revolutions is in fact telling you theta in a roundabout way. And then finally we're given that the torque, the friction torque on this thing, is 2.5 Newton meters. So that's the friction torque. Okay, so a few things we need to remember about this. As far as the exam is concerned, by the way, worth pointing out at this stage that although this question that you're given, the tutorial question, is in 3 parts, A, B and C, in an exam you might well be asked to just find the total work done, which would involve doing parts A and B, even though not stated. So sometimes it's a multi-step process you need to go through. Another few points to make, that again the formula that relates the torque, the total torque, is I, which is the moment of inertia, times alpha. And that's sort of like the equivalent to the linear one of force is mass times acceleration. So these are the related ones. Torque is I alpha, is the angular version of that. And the other thing that's worth remembering at this point is that the total torque acting on the object equals the driving torque, which we're going to calculate, plus the friction torque, which we're given. So this formula relating, allowing us to find the total torque, and this formula to find the torque, I alpha, you're expected to remember. So now let's go through this question and see if we can do it. So first of all, let's have a look at part A, which is asking you to find the angular acceleration. So part A is, if we get the relevant information, because this is the formula that we're going to be interested in, because we know that omega 1 is 0, we know omega 2 is 2 pi times the frequency, and we know that theta is 2 pi times n, the number of revolutions. So we've got omega 1, omega 2, and theta. So we're looking for a formula that involves omega 1, omega 2, theta, and what we want, which is the angular acceleration. So that particular equation of motion is the one that we want. Rearrange for alpha, and then calculate what theta is. See if you can finish that off. Sorry, not theta, calculate alpha. You should get that alpha equals 2.73 radians per second squared to 3 significant figures. So for part B, we've got to find the applied torque, or the driving torque if you like. The applied torque equals I, the moment of inertia, times alpha. Well, we know alpha, we've just calculated it, but we don't know I. The formula is I equals m little k squared, which is on the formula sheet, and we're given k. So we can find I. We're given k and m, so we can find I, plug that in to come up with the value for the applied torque. And see how that might well have been a question in the exam, which might have said, find the applied torque, which would have meant you'd have had to have gone back and found alpha to be able to do that. And you should have come up with an answer of 7.7 Newton meters to 2 significant figures for the applied torque. So for part C, find the work done. Well, we know from, again, the formula we need to remember, work is force times distance. Well, if you think about the angular equivalent, instead of force, we'll have torque, and instead of distance, we'll have the total angle turned to. Well, we know theta, the total angle, and the torque is the total torque. Remember, the total torque is the applied torque, which we just calculated, plus the friction torque, which we're given. So that's the total torque. Multiply that by theta, and we'll get the work done. And when you do that, you should find that you get an answer of about 32,000 joules to two significant figures for the work done. So in this question, if you'd have been asked to find the work done, then you would have had to have gone back. You'd have to have found the torque. How would you have found the torque? You'd have found the angular acceleration, which would have meant you'd have had to have gone back to part A and found the angular acceleration, and then you could have found the work done. So it could be a process of sort of working your way backwards to come up with the final answer.